I just want to clarify, because you will see this on your test. You'll see these words. You'll see the intrinsic or intensive property. You know, I can call it either one. It's the same. This is the same thing. And you'll see extensive or extrinsic properties. So intensive, intrinsic, I always think that means inherent, like something that's inherited. That's a characteristic of that particular substance. Thank you. I'll look at it. Property. It's a property. Okay, there we go. Thanks. All right, so they're going to be independent of the amount of substance I have. So if I give you some water, I can give you a little milliliter of water, or I can give you 2 tons of water. What's never going to change about water? It's still water, so it's still that compound. It's the density of it's still the same. It's still going to be a certain amount of mass over a certain amount of volume, which is just a ratio. It's always going to have a melting point of what? Melting point of water. Are you guys using those F words? Whoa. Celsius. Okay. Scared for a minute. Okay. So the density is always going to be 1 gram per milliliter. Always. It doesn't matter how much I give you. The melting point is always going to be 0 degrees Celsius. The boiling point is always going to be 100 degrees Celsius. Melting point and freezing point are essentially the same thing, because it's just going back and forth between liquid and solid. It's just, are you talking about going from solid to liquid, or are you talking about going from liquid to solid? So the point, though, is the same. It's still 0 degrees C. Okay, specific gravity we'll get into when we get to thermochemistry. But what I'm saying is, I don't care. I can give you an ocean full of water or a milliliter. All these properties are never going to change because it's inherent. And so I like to call those characteristic properties, because that is a true characteristic of that substance. And, you know, that's just going to be a way that I like to explain it the best, you know, and simply as possible. But the real true definition is it's independent of the quantity of matter present. So it's very kind of simplistic there. Okay, extrinsic is just going to be the opposite of that. And that's one where you have a property that will change if you change the amount of substance. So I think those are pretty easy to see. If I have a milliliter of water versus an ocean full of water, what's definitely going to change? The weight, the mass, the volume, those things that are quantitative, those things that are, if you have more of it, you know that matter is going to change the amount of the meaning of something, okay? So it's going to change when you change the amount of substance. So the amount does matter. Does matter. The amount of matter does matter. Come on, guys. Okay. So examples of those are volume, weight, and mass, which would be like grams here. So those are just 2 different definitions I want you to be aware of. And I can call them both extrinsic or extensive. Just remember the X and then the N part. Now let's do one more conversion together. We didn't do this one yesterday. Give you guys a second. You're still working. So we've dealt with joules a lot, joule J. We've done kilojoules and normal joules. And we all know it's just a similar, or it's a unit of energy. And we don't see, most of the time, unless you're getting some funky nutrition labels, on your nutrition labels, you normally see calories, right? All right. Calories are good for what? What do you need calories for in your body? Energy. So it's not your true form of energy, like ATP is actually your true form of energy, but we take those calories and we convert them to ATP in our mitochondria and all that jazz. But it would be weird if you actually knew how many calories were in your food. So how many calories do you eat a day? What's your normal average person's calorie intake a day?
4,000.
4,000? Oh my gosh. You must be an athlete, because that's going to be, people be gaining weight on that one. 1,000 to be like you're anorexic. 2,000, thank you. 2,000 calories a day is what you're supposed to, most average people would intake. A lot of adolescents are going to be more because your metabolisms are really high. But as you go throughout life, you kind of change your diet and change your caloric intake. Because if you have too many calories for the amount of energy you burn, then you pack it on in certain places as fat, right? So who's ever seen, you guys seen the, what's this called? you know, like the Fitbits, they track your calories and stuff you do. So far today, 590 calories, people, in the 2 hours I've been up. Okay, I'm feeling good about my life. All right. So anyway, calories here, lower C calories. If you ever look on a nutrition label, it's not lower C, it's a big C, because big C calories is equal to 1,000 little c calories. So a banana has about 100 calories in it. That's not bad, right? 100 calories is good for you. But that's that's a big C calories. So if a banana has 100 big C calories, how many little c calories is that? How much? Times 1,000, so it's 100,000 calories. If I told you a banana had 100,000 calories, nobody would eat anything. Like, I gotta watch my weight. You gotta keep your figure, right? So they don't put the real calories on food nutrition labels because that would scare the crap out of people. Like, oh my gosh, this cracker pack has 200,000 calories in it. So they always adjust it because the normal average person is not going to understand this, but we do. Okay, so if we really actually had to talk about calories, our bodies burn approximately 200,000 calories a day. That's what 2,000 calories is, which is what the average diet should be. So that's really just an interesting fact. But the calories you're going to be burning. Your brain uses 50% of your energy a day. So if you don't eat something before my class, your brain probably hurts because it doesn't have any energy. Okay, so breakfast, the meal of champions. Okay, all right. So now let's actually do this conversion. If I tell you this conversion, 1 calorie is equal to 4.184 joules, and I give you question, how many joules are in 300 calories? What am I starting with? What's my given? 300. Come on, people, loud and proud. I want to hear you. Okay, 300 calories, and then what am I multiplying by? What goes on bottom?
1 calorie.
1 calorie goes on bottom because you want to cancel out calorie. And what goes on top? 4.184 joules. And that is like 1,200. I'm going to guess something like that. It's probably close. But I'm just not calculating for reals right now. So calories are gone, joules are in. That's going to be what our desired unit was. How many sig figs would I require in this problem? 1. Which of these is your limiting factor here?
300.
Right, there's only 1 sig fig here. No decimal, right? Start from the Atlantic. I'm sorry, decimal absent Atlantic on this side, yeah. So you start from the first non-zero digit. Nope, yes, 3. That's the 1 sig fig. This one has 4 sig figs. So this should be rounded to 1,000 joules. I know it's rounded a lot, but that's because we have really, really inaccurate measurements over here in terms of sig figs. Okay, cool. Moving on. Let's do law of conservation of matter. I'm going to kind of briefly go through some of this. I want to work on the balancing part. I'm going to skip this bit for a second. Okay, so the law of conservation of mass and matter, we all know, whenever it's like the very first day, means that matter is neither created nor destroyed. It's all here. We're all made of that stuff that was made in the Big Bang, right? But stuff can always change form. And changing form just means it's going to be moving around in different compounds. But the carbon that we breathed in from that plant, like outside our house, is going to be put into our body in some way or form, and then we're going to breathe it back out eventually. So we're going to be just changing the way it looks, okay? So it just changes form or is rearranged in a chemical reaction. And that's what the law of conservation of mass says. Now, the law of conservation of mass is always usually referring to a chemical reaction. That's why I want to make sure that we understand it's a chemical reaction. So that underlined part is really the only important part here that you've never seen before. Do not write down every word, or we will be here bored to tears. Okay, so you can see my reaction here. A plus B yields AB. I've just rearranged them, and they're in the synthesis compound now. Or I can have this lower one right here. A and B are together, and then C is separate. And when I have a chemical reaction form, the only thing that's rearranged is C boots out B and takes its place. So B has been removed, and C is now hanging out with the cool kid over here, A. So that's all it is just rearranging matter. We never get rid of it, we just rearrange it. So let's look at an actual reaction. These are just like cartoon reactions. Let's look at actual reaction. Remember this one? Totally Yeah?
Yeah.
See, photosynthesis. You're in my class. Do I have anybody here? No. We did a photosynthesis dance. I'll show you that sometime in our free time. So, first of all, let's break down the pieces of this. What is this thing right here? This arrow. What's it mean? Not equals, really. Makes, you can say, or yields. Those are the two kind of words that we associate. So we say 6 carbon dioxides plus 6 waters yields glucose plus 6 oxygens. So that's the word you use for the arrow. Don't say equals, really, because that's more of a math problem than a chemistry problem. So if I wanted to go ahead and make sure the law of conservation of matter was followed, I'm going to look and see, are all the elements still there? How many how many atoms of carbon are on the reactant side? Yes, only 6, because you see 6 times, you see this imaginary 1 behind that carbon, subscript of 1, 6 times imaginary 1 is 6. So we have 6 carbons over here. How many carbons over here? How many? 6 again, because we have 6 times the coefficient of 1, so there are 6 carbons there, okay? How many oxygens over here total? Reactant side. Shout it out. Really close, but I want you to see there are subscripts here. So the subscripts are these lower numbers down here, and coefficients are the numbers that are big numbers out front, right? So if I see a 2 here, and I have 6 of the carbon dioxides, I have to multiply this number by that number. So how many oxygens in this carbon dioxide, and 6 of them? 12, because I would do 2 plus 2 plus 2 plus 2 plus blah, 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 plus 2, right? So I get 12 total oxygens here. How many in this water here are 6 waters? 6. There's an imaginary 1 after that oxygen. We don't write ones because they look stupid. Just that's the real reason. We don't like to write them because they kind of throw us off. So, but the 6 times the 1 gives us 6 more oxygen. So how many total oxygens? 18. Thank you. 18 oxygens. I'll do it like that so you don't think it's 180. Okay, so how many oxygens on this side? Where do you see them? How many in the glucose compound? Excuse me?
06.
Right, 06. And that's just a 1 coefficient, right? So 6 here. And how many here? 12, because it's 6 times 2. So that's 12. So total of 18, okay? Oxygens. What's left here? Hydrogens. How many hydrogens over here? 12, because you said 6 times 2, because there's in one water molecule, there's 2, but we have 6 of them, so that's 6 times 2, which is 12. And how many here? 12. So 1 times 12 is still 12. 12. Okay, so we had on the reactant side 12 H's, on the product side 12 H's. All right, so what have we just proved? Right, the law of conservation of matter or mass. The law of conservation of matter means we had 6 carbons and 6 carbons. Well, guess what? Carbon weighs the same. It's a reactant or product. So as long as I have all the same numbers of the atoms here and here, reactants, products, the masses then will also still be the same. And we're going to deal with balancing a lot more in a little while. But I do want you to kind of get the general sense of how to count up the atoms. Okay? Okay, so, we just did that. Yay. Okay, so if I'm looking here, I've got a combustion reaction. How do I know this is a combustion reaction? Just by looking at this reaction right here. Okay, I see CO2 and H2O, which we know is a combustion product. But what is that thing right here? What is it reacting with? What is this? This is actually methane right here. What is methane reacting with? Oxygen. Anything that reacts with oxygen is just a combustion reaction. Like we saw in our flamethrowers. Our Bunsen burners yesterday, we had to inlet some oxygen so that we could get the fire to burn, which is combustion. So we know this is a combustion problem because we know we see oxygen there. And then we also see these carbon dioxide and water products. How would I balance this? How many carbons here? How many carbons here? How many carbons on the left side? 1. There's actually an imaginary 1 after this. So if you need to write it for now, that's cool. So 1 there. How many here? 1. Right, 1. So we're good on carbon, right? Okay, how many hydrogens are here?
4.
4? How many here? 4. So I've already balanced the hydrogens for you. I put a 2 in front of this water. So we can have 4 hydrogens. How many oxygens here? 4 here. And how many here? How do you get 4? Right, so we have oxygen here, which has 2, carbon dioxide, which has 2 O's. And then this 2 times the 1 on the oxygen over here, which is another 2. So 2 plus 2 is 4. So we have 4 oxygens and 4 oxygens. That one's harder to see because you have oxygens in 2 pieces of it on the product. So you just have to kind of count them out. So you could actually calculate the number of atoms on each side. I might have you do that on the test just like one time to kind of get the hang of how to show me that the law of conservation of mass has been followed. And then we have more examples showing the same thing, but I've already balanced them for you. So you have 2 AGs, 2 AGs, 1 S, 1 S. So that's something you might be seeing again on your test, okay? So we'll work on that some more too. Okay, oops, I'm sorry. All right, told you I was done. 15 minutes, 3 minutes, okay? So for the Law of Conservation of Matter lab, this one's kind of fun because you get to blow up some stuff. When I say blow up stuff, I mean like air into a balloon, not like boom, okay? So you guys are going to be following the instructions in lab acting. It's fairly simple. I will tell you, pull out a piece of paper, a piece of paper for your lab. I will tell you one tip. The lab, it calls for a 600 milliliter beaker. These babies are heavy. And I say heavy, they're not heavy to us, but our scales, our electronic balances, some of them max out at 200 grams, some of them max out at 600 grams. So depending on how heavy that is, your scale might say error. That means that you need to get a smaller beaker. So I did put some beakers in the baskets that I placed at the lab stations, but of course I use a smaller one. The 600 is just like in case something kind of bubbles up and over, it doesn't come out of the beaker. But if we make a mess, who's going to cry over spilled milk? We'll clean it up, right? So you don't have to use a 600 milliliter beaker. I will show you though on back there how to use the weigh paper and how to use your scupulas for certain things, okay? So I'm going to have you guys open up your lab notebooks to the Law of Conservation of Mass or Matter lab, okay? Lab stations, send somebody get your goggles. And so I'm going to have you make up your quiz today from whatever day.